A very good evening, everyone. Uh, Yesterday we went through k-means clustering, and today's topic that we are going to cover is hierarchical clustering. Right. So let's just take a moment, and what we have on screen is if this is the data that is given, and if I perform a k-means clustering on this data, what would most likely the clusters be like, right? And the respective k values that were used are given here, right? Even though I can very clearly see that here it's just two clusters and again two here, but the way k-means identifies this sometimes are not necessarily how we expect it to be, right? Uh, just to summarize k-means, right? Typically, it is a good algorithm which is able to cluster elliptical data well or spherical data pretty well, right? So this kind of a data, it is able to cluster it well. It's able to define boundaries on very closely knit data, right? But the moment there come some patterns or higher dimension patterns or very closely dense data that might show some other pattern, clustering does not necessarily perform, or k-means clustering does not necessarily work well, right? The other thing that we discussed yesterday is k has to be a input parameter for k-means clustering, right? If we are not providing k, k-means clustering doesn't work, right? It does not help without k, right? Also, we discussed that k-means clustering uses distances to determine which cluster every observation has to get assigned to. And hence, it's important to scale the data before using k-means clustering, right? That's still generic. We discussed this in KNN also. Any algorithm for that matter where we are going to use distance, it's good to scale, because otherwise the features with higher range, they will bias the decision, right? What else we discussed? We discussed that k-means happens to be locally optimal solution sometimes, which means that the result is dependent on the initial means or the cluster means that it starts with or initiates with, which also means that if you do not fix a seed, the results not necessarily be the same every time, right? The clustering results might differ by a bit, right? Uh, I think pretty much we have summarized k-means clustering, and some of the disadvantages or challenges of k-means clustering. I think the first one is that we need to give a k, right? And that happens to be a foremost disadvantage, because most of the times you do not have a number, right? And most of the time you need to, let's say, determine using the elbow curve or using the statistic that we discussed yesterday, which is more about the similarity and dissimilarity. Pardon my memory here. Can somebody help me recollect the name of the distance statistic, similarity statistic that we used yesterday? Was it Siloe score? Right?
Yeah.
So we discussed elbow method and the Siloe score method yesterday. There's another method called gap statistic. Feel free to research about that. But typically, I think these two approaches are enough for us to determine or explain what should be the number of k, right? Another point that I did miss out is that
Sorry
k-means
to
clustering.
sorry to interrupt. Can you talk about distortion scores also? Like in the assignment it was given. Yesterday's class assignment.
Okay, okay. So we'll come to that. Sorry about that, but let me quickly recap this. We also discussed about the iterative process. K-means is typically a iterative EM based algorithm, where in the first E step, typically you determine or assign it to the clusters, and in the M step, you then recompute the cluster means, right? And generally it makes spherical clusters, and K, getting the K is the challenge. I think I'll come back to the question. I have not gone through in depth about the yesterday's assignment. Let me go through that in a bit, and I'll come back to what the distortion part was. Or else, if you have a specific question, maybe I'll be able to explain. But otherwise, let's park it till the end of the class. Okay, cool. So if you guys recollect, yesterday I gave an example, right? That example maybe came a day early, but that is a very perfect example when it comes to hierarchical clustering, right? The example that I'm talking of is me in a Bangalore mall versus a Delhi food court versus, let's say, a London airport, right? I associate myself with the most closest ones, no matter which level I am, right? And hierarchical clustering is exactly the same thing, and you will see why, right? Just to get started, there are two ways in which hierarchical clustering can work, right? One is agglomerative and one more is divisive, right? As the name itself says, agglomerative is something that you are doing a top down, right? You have clusters at the bottom level and you are going top down, right? So this is agglomerative, right? And you finally end up in a big single cluster, right? Divisive is nothing but you start with a big single cluster and go, sorry, this is bottom up and this is top down, right? So you go top down till you get the final clusters, right? So agglomerative is bottom up. You start with smaller clusters or individual observations and you go bottom up. You keep combining these, and we'll see in a bit how we combine, but you keep combining till you reach a single cluster. Agglomerative, you agglomerate. And divisive is pretty simple. You start with all the data, right? And then you make partitions to the data, right? Slowly you make partitions and keep breaking this data into smaller clusters, and eventually you reach the same state, right? So those are the two types of hierarchical clustering, right? And in practice, mostly agglomerative clustering or bottom up clustering is used, right? That is because it's very easy for us to explain it through the metric of similarity score, right? Or a distance metric, which we'll see in a bit, right? And like I explained, I think we have a very good way in which agglomerative is being explained here. So let's assume for a moment I have a data set where I have these 4 data points, right? I have these 4 data points in my cluster. Since it's agglomerative or bottom up, what I will do is I will assign a single cluster to each of these data points, right? So every cluster has only one observation and is represented by a different color in the first picture, right? Then what we do is, as we move up higher, what I do is I find what are the most similar clusters here, right? And let's say for a moment, these two are similar clusters, right? So I club these two. So that's represented by the red line here, or the red oval, right? So what I'm doing, I'm clustering these two small clusters, in this case observations, to form a larger cluster, right? So what I will be left after this operation is one observation, two observation, and a third cluster. Now this becomes a cluster, no more two observations, right? Then the next part is, how do I merge or figure out which of these three entities are similar, right? So it can be this data point or observation, this observation, and this cluster, right? And here it's very clear that these two are similar. So we say, I will take this merging approach, right? The green oval, right? And the final one is the blue oval, where you form a single cluster of all the data points. Again, it is hierarchical in nature more than iteration, and then definitely iterative because you go one level at a time, but it's hierarchical in nature, right? And we'll see that in a bit, or I can explain that, or what I mean by hierarchy here. So let's say if these four were those data points, right? I'm clubbing these two, then I'm clubbing this, and then finally I'm clubbing it to form a single cluster, right? So maybe this is my level 1, this is my level 2, and this is my third level, right? So it's hierarchical because there is a hierarchy, there's a tree based hierarchy. It's iterative because in the first iteration this is what I do, right? In the second iteration this is what I do, and in the third iteration this is what I do. Any questions so far on introduction to agglomerative hierarchical clustering? No questions? Okay. Uh, let's go a bit, let's take a bit deviation again into why this might be important, right? I'll keep adding some of these business things in between so as to uh, get sidetracked by heavy conceptual stuff. So let's say what we discussed yesterday again is typically in real life machine learning solutions, you do more of a serial based or more of a combination of modules. It might be a unsupervised learning or a supervised learning or whatever these might be, but typically a combination of modules to solve any given business problem, right? Typically it's more than one module that's used, right? So this is one ways in which clustering is used, right? Second ways we also discussed yesterday, and we'll also see in one of the examples today, is that clustering can be used on its own, right? To solve some of the business problems. Like discussed yesterday, I want to target, let's say, customers in a credit card company, on whom should I be giving offers to, or if I'm cred, whom should I be giving specific coupons to, or whom should I not be bothering about, or etc., etc., right? So clustering in itself could be used to solve some problems, right? The third thing that we did not discuss yesterday was clustering can also be used to solve anomaly detection kind of problems, right? And it's again, I would, I know I keep coming back to this, but it's more of art than a process, because anomaly detection kind of a problem can be solved using clustering, can be solved using regression, can be solved using encoders, can be solved using a lot of different algorithms, right? Based on how it's structured. So it's more of what kind of data you have. Do you have labeled data? You do not have labeled data? What's the percentage of anomaly do you expect to find? Is it separable in the space that you have data for, right? Just a quick example on what this might be is, let's say if you have, I'll keep a very logical example. I have a 7-year-old fan in my house, okay? What happens, 99% of the times the fan runs fine, right? So if I plot vibration, right? If I just plot vibration, uh, typically the vibration is in this range, right? Typically it's in this range. right? And maybe let's just, for the sake of it, take this as time of the day. Okay? Now, sometimes what happens, 1% of the time when, let's say, there is some issue with the power or very high voltage, or maybe I'm using the fan for a long time, it operates in this range, right? So what I want to do is I want to determine what's an anomaly here, what's the normal operating range of this fan, correct? So that I will use clustering to determine anomalies, right? In this case, it's just these, but there might be few points here, right? There might be a couple points here. So these are anomalous clusters, right? And you can think of multitude of such use cases where anomaly detection could be solved using clustering. You can read more about that, right? Fourth, we also discussed that we can add time series to clustering, right? And we can combine time series or more of TS cluster or time series clustering to have similar time series data into a single cluster, right? Like that, you could also do different variants of clustering to solve different kind of data, right? Uh, why did I come to this is because the choice that you make on, which we'll see in a bit, the choice that we make of which clustering approach to use, what specific parameter or let's say linkage as it's known here, which we'll come to, depends a lot on what you're trying to solve, or what is the nature of the data or the shape of the data that you want to cluster, right? So let's quickly see what we covered. Hierarchical clustering. We said hierarchical clustering can be two types: agglomerative or bottom-up, top-down or divisive. Agglomerative is we start from one observation as a cluster, keep combining similar entities till you reach one large cluster, the blue one in this case, right? And divisive is the exact opposite of it. I start with the largest, most cluster, then what will I do? Which are the most dissimilar, right? So in this case, what's the most dissimilar? Maybe this one. So I will separate this out. I will keep these together. I'll separate this out, right? And in the next step, I'll do the same. Of these three, which is the most dissimilar? Maybe this one. So I'll keep these two together, separate this out, right? And ultimately, I am left with four clusters again, which are individual observations. Right? Uh, in most, or not necessary again, that if you do a top down versus bottom up, you get the same result, right? You, not necessary, and we will see in a bit as to what determines how we combine these, right? Because if it's an observation, it's very easy. How do you combine, right? And I will take some example. I do not know we have it here, but I'll take an example why it is difficult to see how do we combine clusters, right? Any questions on agglomerative or divisive hierarchical clustering? Okay. Uh, let me take four observations, right? Let's say the ID is observation, and I just have, let's say, x1, x2, and x3. I'll take intentionally three features, okay? And I have 1, 2, 3, and 4. Okay. I'll just put some random values. Okay. These are not scaled, but ideally it's better if you scale it out. Now, let's, can anybody point out which of these four are similar? And we are doing bottom up, right? We are doing bottom up. So the first thing that I have to do is, of these four, which are the two that are most similar? Can anybody take a guess?
One and two.
1 and 2. Any other guesses?
One and
Three.
two.
1 and 3. Okay. So how did you arrive? How did
One
you
and
say
two.
1 and how did you arrive and say 1 and 2 are similar? Right? What did you use?
2 and 4. Actually, just a multiple of second. The second row, fourth row is just a multiple of 2.
Okay. So does that mean they're similar?
Yeah, they will be similar.
I actually used
2 and 4.
I actually used
Okay,
Manhattan
so
distance to 1 and 2 similar.
okay. Okay. So you're telling 2 and 4. I'm not telling out what it is, but I've just noted down the two main responses here, right? So I might be bad at drawing things out here. If I take x1, x2, and x3, the three axes, right? Each of these four observations are points, right? So if I say x1 is 4, x2 is 5, and x3 is 1, I don't know how to draw very clearly in, let's say, 3 dimensions, but I'll just make it a try, right? Where would 2 is 5, 10, and 1, so it's 5, 10, and again 1, right? So if you draw like this in 3 dimension, I can definitely say that 2 and 4 will be very far apart, right? By the virtue of its distance, right? So if it's 5, 10, 10 will lie somewhere here, right? Where it will, on projection on x1 will be 10, on projection on x2 will be 20, and on x3 will be 2, right? So the distance between these two will be much higher, right? Maybe they are multiples, but they are not similar, correct? So the reason I brought in this table is, again, we come to the question mark as to how do I say it's similar, right? Now, can anybody think or have an answer? Somebody said Manhattan distance, but Euclidean distance is also useful, okay?
1 and
So
2
right now,
are
let's
similar.
assume, yeah, so by the virtue of that, I think in this case, you either use a Manhattan distance or use Euclidean distance. What we will find is these two clusters are similar, right? Once we have determined that these two, observations are similar, the same question repeats, right? Now, what is similar between this clustered entity and these three observations, right? And even before you answer that question, what you need to do is, first, since now this is a single entity, which means you cannot have two, or you cannot have two identifiers for it, or you cannot have two sets of x's, x1s, x2s, and x3s, right? If I'm telling this as, let's say, entity E1, right? I need x1, x2, x3 for entity E1, right? I can arrive it by taking a mean of the two, right? It is one of the approaches, right? So what I will say, entity E1 lies at the mean of the two observations, right? That's one of the approaches, right? And there are other approaches where I will say I will take the minimum one, right? I will take minimum, or I will take maximum, right, to explain the entity E1, that is cluster of observation 1 and 2, right? Once I have found the coordinates of these E1 based on whichever strategy I choose, I can then repeat the process and find, okay, what's the closest one, right? Maybe in this case, the third observation looks closest by naked eye, and most likely even when you compute it out, right? So what I will say, the next cluster here, right, with numbers might be this, right? The next largest cluster, right? And eventually, since the only one is left out is the fourth one, this will be the final cluster, correct? Any questions on how did we choose to combine the observations?
What did you actually mean when you said
Okay.
minimum and maximum?
Okay, okay. Also, there's one more question. Please repeat once about similar. Okay. So minimum and maximum, what I mean here is just take the minimum value of the x, right? Minimum value of these two, right? Minimum value of these two. That is one of the ways, right? Not the best ways and not the worst ways, right? It's again science, and you call it some other name, it will fly, right? What do we mean about similar is that what if we recollect, what I want to do here in clustering is I have these 4 rows of data or observations, right? What I want to do is, which two should I club first, right? In this case, I have chosen to club these two, but why not I can club these two in the level 1, right? How do I determine that, right? That's determined by how close each of these observations are, right? And what we just discussed, by computing the similarity or computing a distance score here, is that observations 1 and 2, right, are more similar. So essentially what you're doing here is you are computing a distance matrix, right? Distance between 1 and 1 will be always 0, and all the diagonal elements will always be 0. So what you are doing, you are trying to use some distance and filling these points, right? And we'll see that, we'll come to that in a bit, right? But and you will go on combining those so as to hierarchically go up, right? I hope that answered the question, and that's something very similar that we did here, but here we have an example with 5 data points, and this is giving it in a 2 dimensions. So let's hope this addresses the questions, the remaining questions that you may have. Okay, so what I have here is 5 students and the marks that they have achieved. Okay, now I think the first thing that we saw that we have to do here is create a proximity matrix or a distance matrix or a similarity matrix, whatever you call it, right? What it says is, what's the proximity between any 2 observations in my data set, right? I want to take a moment here to draw parallels to k-means yesterday, right? In k-means, we did not compute distance between every 2 observations. We only computed distance between every observation and the cluster means, right? what we also saw is if there are 100 observations and my k equals to 5, so I need to compute 100 into 5, 500 distances. But in this case, if I have 100 observations, I need to compute 100 into 100 distances, right? It's a n squared number of distances that I have to compute. Any questions on this or the analogy or how it's happening in k-means, the distance comparison or computation? And what's important is to have that in the back of the mind that this is more computationally intensive. The number of distances that you need to compute grows exponentially, right? 100 into 100 itself gives such a big distance matrix. Just imagine if you have, let's say, 1 million observations that you have to cluster, what would be the number of distances that you have to compute, right? And in this case, the proximity, I think it's Manhattan distance that's used. Typically, just take a difference, 10 and 7 is 3, and similarly compute all the distances. You could also use Euclidean distance in this case. Once these distances are filled, right, the first thing, or we went through in a three-dimensional plane and tried to see which are similar or closer, but exactly same thing happens here, right? So in the matrix, I try to find which is the lowest proximity number, right? If I ignore the diagonals, which is the lowest? And since this is a symmetric matrix, 1, 2 and 2, 1 or n, m or m, n will be same numbers, right? It's a, if you fold it across the diagonal, it will be the same numbers, right? So what is the lowest number? In this case, it's 3, right? So what it is asking us is, I can club or I can cluster as my first iteration observation 1 with observation 2, because the proximity or the distance or the similarity between these two observations, right, is high, right? Or the dissimilarity is low, right? So I combine these two. So what will happen? These two were separate in the first instance. Now these two become a single entity or a single cluster, whereas the other observation stay separate. Okay. Now we need to update the clusters, right? And again, the same question, 1 and 2, right? They had different marks. If you see, 1 and 2 had 10 and 7 marks. But now when I combine this, the question arises, what's the value or what's the number of marks I will give to this combined entity, right? So I can choose, in this case, I have chosen to take the maximum value, right? We could do a minimum value or an average value as well, right? But I'm choosing the maximum value, right? So now this combination has 10 and these are the rest, right? Now if you again compute the matrix, right, you will see that 1, 2 and 4. So this is the most similar one, right? 1, 2 and 4 has 10. 10 is the oh sorry, there is a 8 and a 7 here, right? So you my bad on that. So you combine those, which is the smallest number, in this case 7, right? So we will combine 3 and a 5, right? So the moment you combine 3 and a 5, 3 and 5 become a single entity, correct? So that's what we are doing here. Now 3 and 5 become a single entity, and you keep on repeating this process, right, till you end up with a single cluster. Okay, I hope these examples and explanation is clear, but let's take a pause here and see if we all understand how does agglomerative clustering work. Any questions? Okay. So hierarchical clustering again has two types, bottom up or agglomerative. That's what we were discussing, and top down, which is more of a divisive clustering, right? Agglomerative, it starts more of combining from observations, slowly going up based on the similarity or proximity or distance, and it tries combining entities as it goes higher, right? And one thing that we did when we combined two observations is that we also update the coordinates of that observation, right? And in this case, we have used max, but you can use min or an average or a median or anything, right? But we have used max here, right? So that's the prelude to our next section, which is, I would say, quite important when it comes to hierarchical clustering. Okay, cool. So the way it works is that once you have a entity, right, and I will again use a drawing here. Once I have a cluster, right, let's assume these are the two observations in this cluster, okay, and it's a two-dimensional problem I'm solving. If there is a data point here and there is a data point here, correct? The way now I can find the distance, right, or linkages as it's called in hierarchical clustering, can be very different, right? And this will form, or the decision that I make right now will determine the quality of clustering that will come out. Okay, so we will discuss few things here. We will discuss what is single clustering, single linkage. We will discuss what is complete linkage, and we will discuss what is average linkage. Okay, primarily three ways that you should be aware of, right? To make it a bit easier to explain each of these, I will have one more cluster here. Okay, one more cluster here, right? Now I have totally three entities, right? This is entity 1, this is entity 2, this is entity 3, right? Of these three entities, 2 are clusters and 1 is an observation, right? So what happens in single linkage, right? What happens in single linkage is I try to find what's the minimum distance. What's the minimum distance, right? So if I have three entities and if I compute the matrix, the proximity matrix, this will be 0. So I need to just fill these values, right? Or rather, this also will be 0. So I just need to fill this, right? So what will happen is that the moment I have these three distances, you can fill in the matrix and then decide, right? What is happening? The single, what it is it's the smallest distance between the entities, right? You see, I have taken the smallest edge or the nearest edge, right? I could have chosen to choose this edge or this edge versus this edge, but have taken the smallest one, right? That's the single linkage, right? Complete linkage is opposite, right? I take the farthest edge, right? I take the farthest edge to determine the distance, right? I take the farthest edge. average linkage is essentially I will take the distance between every point, right, and average it out. So let's say I'll take D1 and D2 here and average it out, right? When you are comparing these, there will be 4 distances, right? So I'll average D1, D2, D3, D4 in this case, right? Same thing here, D1 and D2, I will average, right? So that's the average linkage, and that's how you will fill this matrix and you will take the decision, right? Let's see how it works. I think same thing is explained here. In single linkage, let's quickly revise. In single linkage, I will take the minimum distance between 2 entities or clusters and fill in the proximity matrix. Okay. In complete linkage, I will take the maximum distance, right, and fill in the proximity matrix. And in average linkage, I'll take the average. I'll take all possible combination distances and I'll take the average of that and fill in the proximity distance matrix. Okay. Now, based on how you choose or which linkage you use, some of them have pros and cons, right? And it might be a little difficult to understand why this is a pro or why this is a con. Till the end, because I will show you a picture which will make hopefully things clear on why this might be a pro, right? So let's first start with the single linkage, right? For single linkage, we use the minimum distance to find the proximity matrix, right? The pro of this is it can separate non-elliptical shapes very well, right? As long as the gap between the two clusters is not small, right? Non-elliptical means if there are clusters of different shapes and they are far apart, a single linkage will be very effective for us to find clusters in that, right? The disadvantages of this is it's that it cannot work well if there is noise in between the clusters, right? What I mean by that is there is some form of continuity between the clusters. This might not work very well, right? And if you think out intuitively why it will not work is the minimum distance will always be between the noise of the clusters, right? It won't be between the core of the clusters, right? And in terms of it's very greedy, right? It takes the nearest distance, so it might prematurely merge two clusters based on just two observations which are close to each other, right? But the core of the cluster can be far, but it might prematurely merge those. Okay? So this is the single linkage, sometimes also referred to as minimum linkage, right? Since the minimum distance between two entities or clusters is used. On to complete linkage, where we to fill in the proximity matrix. The pros of that is that it does a good job when there is noise in between the clusters, right? When typically in real life data, what you'll find is it's not very separated, right? There is noise in between the data. So this does a good job in separating or defining the clusters there. It is more biased towards globular clusters or spherical clusters, spherical in 3 dimensions, but globular might be in higher dimensions, right? It is more biased. The clusters that come out are more globular in nature, right? One of the other cons is it tends to break large clusters, right? By the virtue of how it works, it even though from a density perspective there is a very large cluster, this tends to break it. It will not keep them in a single cluster. It will break it. So that's one of the cons, right? The average linkage, what we discussed, the third one is that we take the average distance between every observation in the two entities or clusters and then take the average, right? And this is a direct distance or a Manhattan distance, right? It's not a squared distance. We just take the average and find out or fill the proximity matrix. The pros again here is, if there is noise, then this does a good job, because what it's doing is it's computing distance between every other point, right? So even if there is noise, that might not bias the decision that which cluster should I merge with, right? It takes in a vote from every member in the cluster, right? The cons can be again biased from a globular cluster, and in terms of the centroid, the distance between centroids are very similar, right? So this is not so again popular, right? One of the easier ways, right, to remember this is again a very funny analogy, but think of this as the most youngest child in the cluster choosing which movie to watch, right? Typically, their decision is very impromptu. Their decision is very greedy in nature, right? Little kids, right? So think of this, that's a single linkage, right? The complete linkage is that you take the vote of the most elder person, right? You are covering the most elder person or the most outward case in the cluster to make that decision as to which movie to watch or what to eat for dinner, right? But average linkage is you are asking every person in the cluster on what is the decision, kind of a thing, right? And based on that, a decision is taken. That's a very I know not very good analogy, but it works in this case, right? Any questions on the three linkages that can be used in hierarchical clustering? We'll take a pause here for a minute.
What do you mean when you say like it's biased towards globular cluster?
Yeah. So what I mean by bias towards globular cluster is that when I say bias, is that in 2 dimensions, if I have to draw, the cluster will be a circle, right? In 3 dimensions, if I have to draw, it will be a sphere, right? It will be a sphere or a kind of a cricket ball kind of a thing, right? Typically, since you are using the large, or let's say if you're using an average kind of a thing, you are computing with everything else, right? So the way clusters are created are more of a globular, because if there is a data point just outside of the globe, that might belong to some other cluster. So the clusters that come out from these linkages where it's a con, typically we'll see it's a globular cluster. Did I answer your question?
Yeah, I can understand that average can have globular clusters, but how come that complete linkage is biased towards globular cluster?
Correct. So I think again it's how far you can visualize in 2 dimensions. If you recollect, right, here we have a made up case on how does it work. But if you recollect, right, I'm starting with 4 observations and I need to map these observations, right, at every level based on how it works and finally reach, right? So let's say if I can draw some things here, right? The way it will work is, maybe since this is a hierarchy, this is the first thing that it will attack, right? and maybe this is the second thing that it will attack. But eventually what we will see, this will become a tree, right? This will become a tree. What I mean by tree is maybe something like this. Right? This part are these observations. Okay. By the virtue of longest distance, what will happen is that the other clusters that are formed will also follow such pattern, right? Will also follow such pattern. The way the distance will figure out the proximity, it will give more of a spherical clusters. And let's say if you just take blobs, something like this, right? So these are all data points and these are data points, and try to use hierarchical clustering with complete linkage, you will see what happens. Or let's say data points of this area, right? To understand clustering, I think this is one exercise that I would recommend all of us to take is make blobs, and I think these blobs are by default available, some 5 or 6 different shape of blobs. Try to apply every clustering on that, right? Try to apply every clustering on that and see the result, and try to interpret as to why k means is separating this into a cluster and this into a cluster, right? The answer might not be very intuitive, but once you spend some time thinking through, uh, it will be clear as to how the mathematics comes up and shows up in some of these patterns, right? So uh, I think it's honestly it's difficult to explain or intuitively say how does it make sense, but if you may take some time out and take some examples and take it, or maybe take a random data or fabricated data and try to solve it, it might help you with some intuition as to why it is being like that, right? And at every step, maybe you can take out the proximity matrix or the distance and try to see if you're able to interpret. That will help you to get a clear understanding of why is it clubbing those two entities. Cool.
Okay.
So each of these have, as we saw, have their own disadvantage or advantages, right? Usually every hierarchical clustering uses what we call as a Ward's method, right? Ward's method is very similar to the average linkage. The only thing is, instead of taking a Manhattan distance, we take the squared distance, right? It takes the square of the distances, right? Sum of squares. That's what is Ward method for us, and this is a default in hierarchical clustering as well. Okay. Again, pros, it's that it works well in clusters, and cons is that again creates globular clusters, right? And to your point, Smriti, I think if we see these data, right, and that complete kind of clusters it's creating, right? It's always circular or spherical in nature. So even if the data is not spherical like this one or maybe this one, the clusters that it's forming are more of globular is what I would call, right? Whereas if you use a single linkage, right, see how does it work on these, whereas single is not working great here, right? Complete linkage is working well on data which is globular in nature, but not working well on data which is not globular, or has some pattern in it, specific pattern. Okay. And this is a textbook use case where you will find such data in real life, and every method works well there, right? I know it might be difficult to combine the distance or the linkages that we just discussed. Single linkage is the minimum distance, average linkage is the distance of everything and taking an average, complete is the max distance, and ward is the squared distance between every observation, right? But the results that it provides are very, very different, right? So let's say if this is the nature of your data, and if you use average or complete or ward, you might not get necessarily good result. You might be ideal to use single linkage, right? Similar, if it's a half moon shaped data, you might be good with single linkage. The other ones might not be great, right? If you have very noisy data, then single linkage is not great, right? You have to use wards or complete linkage for it to separate it out for you, right? So that's how you will choose which linkage to use. Most often, the practical scenarios, your data is, this is again very rarely you will find such patterns unless it's generated by, let's say, some machine or electrical or electronic or a mechanical equipment, where due to some frequencies at which it works, it generates these patterns. But again, very, very rarely does it happen. Typically, this is how these are the data that you get to see a lot in real life problems. Okay. Any questions? Let's take a break and yeah.
Yeah. So in agglomerative clustering, like how do you decide at what point you should stop combining clusters? Like how do you decide the key value? As
Correct.
it means we had the key value, but here we don't give the
Correct.
key value, right?
Exactly. So that's one of the advantages. We do not have to worry about that right now. So the way agglomerative clustering works is it always starts from the lowest level. It goes all the way to the top, right? To answer your question now, how do I determine what's my K? We will come to that in a bit, right? But the way the algorithm works is it always gets to the single most cluster, which is nothing but all the observations in the single cluster. Okay. So if I may say, the answer is left you. If you want one cluster, you can choose that. If you want two clusters, it gives you that. If you want four, it gives you that. If you want any number, it gives you that, right? But there is a slightly more mathematical way to determine what's the most optimum number, and that's also we'll cover in a bit.
And then I have one doubt. So in this case, we have a 2D data. We can say that each data point is associated with 2 dimensions. So in there might be case more than 2D. 2D. How do you like? In this case, we can easily visualize this. Our data, the clustering is not properly working, and we can check for various clustering techniques like average and single and those type of things. But in case of multidimensional data, how do we decide which to use, which one to use?
Correct. So in case of multi-dimensional data, see, there are a couple of ways that you can get a hint or get an idea. Okay. Does not work always, right? What you can try is, one thing is you can try to bring that to a lower dimension using principal component analysis, or let's say encoder decoder, and take the center layer, something of that sort. Try to reduce the dimensions, bring it to a 2 or a 3 dimensions, which you can visualize, right? That is one way that I can say. The second way is typically you can try some of the common and see, if you're talking multi-dimensional, right? These patterns will not occur in a multi-dimension. Can you imagine maybe 3 dimension you can still imagine a moon, right? But can you even imagine a moon kind of a data set in a 4 dimension or a 5 dimension, right? It's very difficult for us to even imagine that. So in some of those cases, you typically stick with var distance or average distance, right? And again, based on how noisy your data is or kind of a thing, you determine. But typically, you try to reduce the dimensions and make a educated guess on which one to use.
Yeah, that makes sense. Yeah, thank you.
Okay. Let me take a minute here. We'll go to the clustering page. I actually want clustering to come up, right? So yeah, this is clustering, right? And there are a lot of other clustering algorithms, right? There is Gaussian GMM based, Birch optics, DB scan or density based, agglomerative, spectral, mean shift, affinity propagation, and mini batch k-means. Of these, maybe we would have covered 3 or 4, right? We have covered mini batch, we have covered spectral yesterday, ward and agglomerative. We have discussed DB scan but did not cover it in detail, but we have covered some 3 or 4 in this, right? If you again see, some algorithms work well on some data, correct? Some algorithms work well on some data. The reason I'm putting this on the screen is for the yesterday's interview question, right? How do you determine which algorithm to use, right? I do not run everything in for loop and choose the one which is best, but it is more on what am I expecting, right? And I think also this stands to the previous question, right? That what's your data again, right? Suman, if it's location data, geo coordinates, latitudes and longitudes, I will go with Watt's distance, or I will even go with k-means, or maybe I will use only hierarchical there with Watt's distance, because lat long directly, if I try to compute the distance, it might be wrong, right? So what I will do here, instead of k-means, the way I will compute the distance is not directly by taking lat long and taking the satellite distance, but I will take the road distance, let's say in this case, right? And feed that distance to hierarchical clustering and let it give me clusters, right? Or I will use a density based clustering and I will pass in the uh, distance data to that, the physical or the road distance data to that, right? And let it cluster, right? If I give k-means, most likely it will not give me a good result, right? So that is another way in which you can take a decision, right? And that opens up another very interesting thought, right? That in hierarchical clustering, technically it is possible that you start with the proximity matrix, which is always a square matrix. Okay, technically or logically, if and I think some implementations of hierarchical clustering even allow a proximity data as input, right? Instead of a data like this one, instead of taking a data like this, you can say take this data, which is the distance data, right? And cluster, correct? This opens up a lot more possibilities because the choice of the metric that you use is with you, right? I can choose a Manhattan distance, I can choose a Euclidean distance, I can choose a physical if it's geolocation. I can choose, let's say, a Gover distance, which again is a very important distance, and all of you should go through that. So what Gover distance does is, let me take a minute to just introduce you if you guys are not aware, is that in a Euclidean distance or a Manhattan distance, everything has to be a continuous variable, right? Every feature has to be continuous, and then you take some squared or Manhattan or something. In Gover distance, what is it logically does is it combine it. It's a way of converting every variable, like a true false variable or a ordered or unordered factor variable. Sorry, factor is an unordered factor like a state or a gender. Numeric is a continuous, and ordered is a more of a level, right? Low, medium, high, or severity, right? It provides a way in which you can compute distance between each of these or separate things, and how you can combine all of this and find a distance, right? So what I'm trying to say here is, let's say if one of the observations or the data set has columns like gender, right, has true or false column, right, has a ordered level column, has a numeric column, right, and I want to cluster on that, k-means might not work, right? It will rather not work. The moment you try to convert that into dummies and stuff, it will explode, right? The number of columns will increase, and we know that k-means with number of columns the effectiveness goes down. But with Gover distance, what you can do is you can take the data set, apply Gover distance, and find the distance between two observations. Let's say in this case it was a person p1 is me and p1 is somebody else. You can use Gover's distance to find a similarity or dissimilarity between the two, and pass this distance to hierarchical clustering and cluster it, right? Which might not be possible in a k-means kind of an algorithm, right? So this is another way in which you could say, how do you choose what algorithm to use? Okay.
Okay, in this case, we're
Cool.
talking about similarity. So, similarity means cosine similarity.
No, Gover is not cosine similarity. It's a distance metric. So Gover, you guys can read about it. I think you will also find a paper. This guy, he came up with Gover's distance, where you can measure distance between two observations of data, where the features can be different data types. Like one feature can be logical, one can be factor. Cosine similarity is something different, right? Cosine similarity is more applicable when you enter NLP space, right? Where you vectorize everything and then try to find out distance between two vectors or angle between two vectors. Okay, this is a very simple approach. Just go through this. It seems slightly complicated here, but very simple. Say for example, the logical, the distance is, if both are equal, then it's 1, otherwise it's 0, right? And on factor also it's very similar. In order, it tries to convert the levels into indices and takes a difference kind of a thing. So it's pretty simple. And numeric, it's the normal distance that it takes. Then you finally give a weight to everything and compute the final distance, right? Cool. Sorry for deviating there, but I think that's an important concept, that for hierarchical clustering, you could bring in just a proximity matrix from any of your custom computation and apply clustering on top of that, right? Not every algorithm gives this flexibility. Okay, cool. What we will do now is just take an example and go through how we do hierarchical clustering. And as a process of that, what we will also see is, how do I determine a good K, right? Or what's the, at least from data, what's a good number of clusters? Right? So what I have here is a data which has annual income and spending score. But I think what we want to cluster here is primarily annual income and spending score. So 2 dimensions. Okay. We'll be mainly using these 2 dimensions to cluster this data set, and the business has given us that business thinks there might be 5 clusters, right? And the 5 are defined as follows from a business angle. So this is the business input that they have given. So these are the careful people who are like, they have a very high income but they don't spend much. Standard is they have average income, they spend average. Target market for Gucci is that they are high income and high spend, right? So typically who buy a lot of luxury brands. Careless are low income and high spending ones, where their income and spends are very disproportionate. Sensible ones are the ones which are like they know to stay within their limits kind of people, right? And on based on this data, Gushi has said that can you help figure out who those people are, right? And this is the customer profile that they have given or shared with us. Okay. And if you see the data types of these 2 columns, they are all integers. Okay. We first take only the 2 columns of interest that we want, and we create a hierarchical agglomerative clustering. We will use the Warts distance, right? And what we can also do is you can plot the data, right? This is another advantage with hierarchical clustering, that I can exactly see and visually inspect how close is this observation here from this observation here, right? Where do these 2 meet? So let's say the similarity between these 2 is this long path, right? But let's say if the same question is where do this one and this one meet, the path is a relatively shorter path, right? So the similarity is lower or similarity is higher, dissimilarity is lower in between these 2 observations, right? Each of these points that you see here are observations or customers from the above data set, right? Just want to take a bit time here and see, because we are seeing a dendrogram for the first time, and how we created this, right? So this happens to be observation. Every point here, this is an observation, this is an observation, right? The path between these 2 says how similar they are, right? But let's say the distance between this point and this point might be that a longer path, right? So it means they are not so similar. Those 2 observations are not so similar. Okay. Is this concept clear? And how we are plotting the dendrogram clear? It's just the visual representation of which are similar and how did we go on adding layers to compute this. Started with each observation, ended with a single data set at the top. Questions? Okay, cool. I believe we do not have any questions.
Please repeat this again. This graph.
Okay. So repeat the dendrogram again. Fair enough. Let me use this to, 1 second, to draw it out to see how we constructed the dendrogram. Okay, I think we covered it briefly, but let me explain how we cleared it. let's say I have, these are each individual observations. Okay. These are 6 or 7 individual observations, right? Let's name them 1, 2, 3, 4, 5, 6, and 7, right? So by definition, what we will first do is we'll compute the proximity matrix for this, right? So 1 through 7, 1 through 7, the diagonals will be 0. We will fill the lower diagonal matrix, right, with the distance. Let's say we are using Ward's distance, right? Now, based on this matrix, we figure out that, let's say, 4 and 5 are the most similar, right? So I will join these two, right? This becomes a single entity. Okay. Now again, I have 1, 2, 3, 4, and 5 observations, and the 6th entity here. I will repeat the process, right? 1, 2, 3, 4, 5, and the entity E6, right? Diagonals are 0, compute the distance. Let's say I figure out these two are similar, correct? Maybe then I figure out these two are similar, right? Then these two are similar, then these two are similar, and then finally a single cluster, right? So this is what we call as is a dendrogram. It's a visual depiction of how the iterations happened, right? And I can say that this is a similar cluster, right? This one is a similar cluster. At the same point, maybe there is a similarity in this area, right? There is a similarity in this area. There is a similarity in this area, right? However, as we go higher, the similarity reduces, correct? So that's how you interpret a dendrogram, and it's very intuitive on how it's created or plotted. Okay. What else? Did anyone observe the y-axis on this chart yet?
Yeah, I just saw its Euclidean distance.
Okay. So what do you think that might represent? I want you guys to answer this.
You know, I mean,
Think through
change
what
in
are we
the
computing and what it might represent. Go for it. It's okay if it's a right or a wrong answer.
I mean, as we could say, like as the Euclidean distance increases, the similarities are not that much in between the clusters. So, like as we Euclidean distance are increasing, they are more unsimilar with each other. So that would be one
Correct.
thing.
Correct.
So I think
Correct.
so when we
So-
merge two clusters,
Yeah.
so it's like the distance between the first two points and the merged
Correct.
one. After merging, what
Correct. Correct. Right. So I think you guys are exactly spot on. What it means is that this group of cluster and this group of cluster, the distance between these two is quite high, right? Which means these two, even though they are directly connected, they are quite far apart, right? If it was a 2-dimension, I could say one stays here and one stays here, right? I'm combining these two because the other clusters, maybe they lie far away, right? So these two are similar, but they're still far apart, right? That's the interpretation. Whereas maybe these two subsets, they are closer enough, right? These two subsets are closer enough. right? Now we will use this information. We will use this information to see, can I have 20 clusters? Can I have 5 clusters? Can I have 3 clusters? Or can I have 2 clusters? Right? So again, it's very intuitive, right? What I want to have, by the virtue of definition, I want a cluster to be similar within itself, dissimilar to others, right? So I want to keep the distance between 2 clusters as maximum, right? So what I will do is, wherever I see maximum long lines, right? So I see maximum long lines maybe at this level, right? At this level. If I sum these lines up, I might end up with a maximum distance, right? So this is one cluster, right? This is another cluster. This is another cluster. This is another cluster, and this is another cluster, right?
So then one more thing. So why the clusters are like one cluster is plotted red and one is green and one is light?
That's a good question. I do not unfortunately have an answer to that, but it might be that it's trying to say that maybe this is the right thing to do. Okay, it's trying to say this is the right thing to do, right? Because the similarity is also pretty similar in this case, right? That might be one of the reasons. But however, I want to just give a business angle to this, right? So remember, when we started, business had said that I want you to cluster them into 5 clusters, right? This provides you a opportunity to see which those 5 can be, right? You can choose this one and the other 5, or you can put a line like this one, which breaks these clusters into 5 clusters, right? So that's a possibility. So yeah, I think here also it's this. I need to get to why the coloring is like this, but this is the ideal clustering, because the sum, as you can see, the sum of the vertical lines is the maximum in this case. Okay. Any other questions related to dendrogram? And always remember, it might again be confusing. This looks like a decision tree. It's very, very different. Decision tree is a supervised algorithm. Hierarchical clustering is an unsupervised algorithm. X in a decision tree is nothing, right? Because you stop at leaf nodes. X here is every observation. Y here is Euclidean distance. And even though there is no specific Y, but you can just bring in the value component on how you split the tree, right? What's the value add by making that split? But there is no Y axis per se. There are no axes in a decision tree, but here you have axis. In a decision tree, you want to split the data by a Y, right? In which you are finding similar fragments so that the homogeneity in Y increases in every subset or a leaf. Whereas in this case, there is no Y, right? You are using a proximity metric or a distance metric or a similarity metric to get homogeneous clusters. Okay. Let's take a quick recap. We are almost at the if I'm not wrong. So where we started with hierarchical clustering. We said we can do either bottom up agglomerative or top down divisive. Then we took some examples of how agglomerative work. We start with observations, compute the proximity distance, keep combining till you reach the topmost part, right? Then we saw what are the different linkages. We have single linkage, complete linkage, average linkage, and ward distance, right? Single linkage, as we say, is the nearest distance between two entities or two clusters. Complete linkage is the farthest distance. Average linkage, as it says, is you compute distance between every observation in the two clusters and determine the proximity. And the wards distance is very similar to average distance, but you use sum of squared distances in that case, right? We also saw some examples on how each linkages can cluster different kinds of data, and saw a visual representation in 2 dimensions. We also discussed that there is a possibility that hierarchical clustering can take proximity data as input, which means you can define your own distance function, get distance between all the observations into a square matrix or a data structure, give that input to a hierarchical clustering, and it will be happy to process and find clusters for you. Right? Then we came through dendrogram, which also helps us to determine what's the optimal number of clusters. It is a good visual representation also, and it also helps you to sometimes apply business. Let's say if business is forcing for a 3 cluster, I might forcibly agree to cut here, right? This is the most logical thing to do that I can try, right? It also depicts how the observations get combined to each other and eventually become a single cluster, right? There is the example that we started, and I think we are just trying to find those 5 clusters now. And we are using agglomerative clustering with Euclidean distance and ward. And the moment we plot it on X and Y axis, here we are again, remember we discussed profiling variables and clustering variables. In this case, we are profiling on the same variables, right? I clustered using spending score and annual income, and I am profiling also on the same variables. Sometimes I might profile on different variables, but in this case, I'm profiling on the same variables, right? And I can very clearly see that this is the careful bucket, right? They are low income and low spenders. These are the target market, high income, high spenders, right? So it becomes very clear on how the clustering is like, right? Now let's spend again, we'll go at a very high level and just mishmash clustering a bit. Okay. Sometimes, or a lot of times, you can combine clustering algorithms themselves to get you a better cluster, right? And the way you would want to do is you want to use the pros of the algorithm while ignoring the cons, right? So let's say the pro of k-means is that it's very fast. It can take hundreds of thousands of rows of data, provided the number of columns are limited. It can give me a fair enough cluster, right? And I'm giving out possibilities that you can do this. There is no right or a wrong way, right? Let's assume for a moment the data given to you has 1 million rows, right? Business has told you that I want 17 clusters in these 1 million customers, right? If you do k equals to 17 on k-means, you might answer the business question directly, right? And as we discussed yesterday, this might not be the best thing to do, right? Because the way k-means works is the moment you say 17, it will just find 17 clusters which are similar to each other and is similar to each other and just give a result. It's not a wrong result, right? It might not be optimal, or it might not be the one in which business can effectively take a decision, or some clusters might be very small, some might be large, etc., etc., right? What you can do is take these 1 million data points, right? Maybe create 100 or 1,000 clusters, right? A small number of clusters. Reduce 1 million to a smaller number. Right? Once you have these clusters, apply hierarchical clustering on the clusters itself, right? So the way you will start is, instead of each being your observation, each thing here will be your cluster itself from k-means, right? This does not work in every example, but this works a lot of times, or this works in very many use cases, right? And then you will combine these based on, let's say, some distance or something like this, right? And eventually when you have a tree, right? And let's say 17 is this, so this becomes a cluster, which means all the observations in this is one cluster, and you will use this to cater to the business needs. Okay. A lot of other things you can also do the reverse, right? Especially when the number of observations are less, what you can do is you can use hierarchical clustering to get an initial version of k clusters. Let's say if you have k in mind, you use hierarchical clustering to get k clusters, initiate them. So k means initiate them with these k centers and run k means, right? Because con of k means is I need to, or it's not globally optimal, right? So giving it a good initiation might make it better, right? So that is another way that is practiced in business. So and there might be many more such ways in which you can crossbreed algorithms or build a pipeline, and it is left to your imagination. As far as you are logical, as far as you can defend why you are doing it, everything is right, right? There's no right or a wrong answer. You just should be able to defend it in a logical and a mathematical way. Any questions before we proceed? Okay. So let's quickly recap the different linkages again, right? And this is just a summarized view of the pros and cons so that it's a bit easier. The minimum linkage, right, can separate non-elliptical shapes, which is non-circular shapes, very easy, given the distance between them is not very small, right? They should be further apart, then it can easily separate that out. But the problem is, if there is a noise, this doesn't work well, right? There is noise, it doesn't work. Whereas the max, it works well if there is noise, but then it tends to make globular clusters, and it also tends to break large clusters, right? Large globular clusters, it will break into two or multiple. Group average, it does work well if there is noise, because it's taking vote from every other observation. Again, it's more biased towards globular clusters, right? VARTS also does a good job on the nice, and again does a bias towards globular clusters, right? And we have seen again at a kind of a data level on how each of these, let's say, if I quickly need to go back, this is a non-elliptical data, right? It's a non-elliptical data where there is no noise and single linkage does a good job, right? There is a lot of noise here. There is a lot of noise or close points here. So it does not do a good job. Again, less noise, it does good job. That's how you try to relate to it, and also try to think through as to how does it determine these two as the distance. It might be difficult because it's more of a iterative hierarchical process, so it does not reach a point where these two are there, but it starts from every observation and then reaches this point. But that's how it works, right? And the last thing for today is a very high level comparison between k-means and hierarchical. K-means is very simple to understand, easily adoptable, works well on small or large data sets, right? Because the distances that I have to compute is not n squared, right? It is n into number of clusters k, right? It's fast and efficient. I can use a batch version of k-means if I have to apply on millions of rows of data. The disadvantages is that I need to specify my k. Another disadvantage also is that as the number of features increase, k-means might not necessarily be a good algorithm, right? On the hierarchical clustering, the optimal clusters can be obtained by visualizing the dendrogram. It provides a good intuitive way for us to make the decision. It shows how each observations are getting clubbed iteratively to get to that final single cluster. It's not great for large data sets because the complexity increases, but then there are ways in which if you have to use hierarchical clustering for whatever reason, you could use some of the ways that we discussed today, or maybe there might be much more hacks to see how that can be used, or even with advancements in compute power, there might be direct ways to use that as well, right? K-means does not take distance as an input, right? It takes raw observations as input because it needs to compute distance between observation and centroid. Whereas in hierarchical clustering, you can provide distances as inputs, right? That's a key differentiator as well when it comes to applicability. Not many parameters here, only k is a choice that you have, unless you choose a different kernelized k-means. But here you can choose between the different distances or linkages that give a very different end result to the clustering. So I think that's it for today in terms of the content. If there are no more questions, we will go for the quiz today. Any questions from today or yesterday?
You talked briefly about the kernelized.
Hey, sorry, Rajat, your voice was very feeble.
Yeah, I was asking, like, you talked briefly about kernelized k-means. So what is
Correct. Correct. So I think we covered this yesterday, right? And even it was there in the exercise, or not the exercise, but the notebook itself, that I think the example that we had chosen was the half moon. And when we apply a k-means on half moon, it does not really work well, right? It does not work well. So what you can do is you can use spectral clustering, which is a kernelized kind of a k-means, where you are taking the data to a different dimension and applying clustering there, right? So it is a kind of kernelized k-means because you're using a different kernel. You are transforming the data from original dimension to a higher level dimension where the patterns are clubbable.
Yeah.
Okay. So let's get to the Kahoot. Before we get to the Kahoot, there is no assignment today, but one mandatory assignment from AlmaBetter is that take a stab at writing an article on clustering. But my personal advice is that before you write that article, explore some of the clustering techniques that definitely what the ones which we have discussed, but also a few that we have not discussed, right? Do not just take one data set and do, but take a few different blobs and maybe a few different real life data sets. Practice on your own and try to see what works where. Also try to make some intentional mistakes, right? Do not scale the data before using k-means. See how the result comes, try to plot that, right? That helps you in building the intuition to how to spot errors when you see a k-means or how when you see a clustering output in plots. How can you spot errors, right? So try to make intentional errors and see what the result is. That will also help you to figure out what's the right thing to do, right? And once you are fairly confident, gone through the content exercises, the homework for today is to write an article on clustering.